Hey, John Gilroy here. It's been estimated that the United States is going to invest $2 billion in quantum computing here in 2024. Well, China is going to invest $15 billion. What could possibly go wrong? Hit the music, Manny. Welcome to the Federal Tech Podcast, a podcast that connects you to federal technology leaders. My name is John Gilroy, and I will be your moderator. Our guest today is Murray Thom, Vice President of a company called D-Wave. You can find them at dwavequantum.com. Quantum, Murray, you must have a big brain to talk about quantum technology here, huh?
You're very kind. Yeah, well, I'm learning every day. It's a challenge, and it's a fun space. So I definitely enjoy working in it.
You know, I've done so many interviews, and people, they tend to maybe enhance their qualifications, and the numbers are a little fuzzy. So I did some research on you guys. I mean, you guys have been around for 25 years. I mean, you got, 200 patents. You got, 180 employees. And it's like, if D-Wave, you got a reputation here. So I wanted to bring you in, and maybe for the benefit of our federal listeners, if they hear about D-Wave or someone talks about quantum, maybe they can visit your site, watch a video or something, and learn more about it. Because, if I've learned anything, is that if a company can survive 25 years, they're either real smart or real luck. Nah, they're not lucky. You got to be real smart, because ups and downs and all kinds of technology changes. So tell us about D-Wave, and more importantly, how can you folks help my federal audience?
Yeah, absolutely. Well, so D-Wave is a full stack quantum computing provider. So we build quantum computing systems. We provide access in the cloud through our Leap Quantum Cloud platform. We have an open source programming toolkit, a software development kit for Python programmers to use our systems. And we have a launch program that helps people sort of along their journey accelerate to identifying the applications for quantum computing based on the challenges, the mission problems that they're working on, all the way through to deploying them into production. And, we're also on a mission, particularly me personally, in terms of helping people to understand quantum computing and the transformational impact it can have for them. Because I think that it's not something that we get to play with when we're growing up. It's sort of a really subtle way that the world works. We now have the world's largest, most highly connected programmable quantum systems in the cloud right now. Any of the listeners in the US and 41 other countries around the world can sign up and get free trial access to begin experimenting with it. So it's a great opportunity for us to learn more about how the world works, and then how we can harness that as an engine to help us solve really hard problems.
I just finished Mary Beard's book about Roman emperors last night, and it was a fun romp. And when I think of classical music, I think of Mozart. When I think of the classics, I think of, maybe Plutarch or Seneca or something like that. But when I say classical to Murray, he goes, oh, yeah, classical computing. He doesn't think about Mozart or Beethoven. So let's set the stage here. You got what Murray would say classical computing, and contrast with a different type of computing. Let's paint the broad picture here, Murray.
Yeah, absolutely. So all of the computers that we use on the planet, our phones, everything like that, they're actually doing something very simple and understandable. They're taking every problem they're trying to solve and breaking it down into simple steps of addition and multiplication. So it doesn't matter if you're using an iPhone or you're developing driverless cars, all of that's getting broken down into addition and multiplication. So all the things we're good at break down into that very well. And, sometimes there are applications where there's a lot of overheads. You have to build a large scale system. That's kind of what's happened in artificial intelligence and machine learning. But there are problems in the world for which those problems do not break down well that way. And those are problems in logistics, in optimization, transport routing, those types of challenges, and the sort of things that we struggle with, workforce scheduling. And quantum computing is harnessing these quantum effects as a resource for a computer. So the notion here, what is a quantum computer? It's just using quantum effects to accelerate calculation. And you can think about it a few different ways, because there's different models of quantum computing. In some of the models, it harnesses the quantum effects to allow the computer to store more information and process over it. And that's going to be really important for driving applications like quantum chemistry or fluid flow calculations and modeling and that kind of thing. Another way to harness the quantum effects is to allow the computer to move between solutions more quickly. So if you're working on an optimization problem, if you're assigning employees to shifts and stuff like that, there's lots of many different combinations of ways that you can assign employees to shifts. So moving between all those different options to quickly find one where you're getting the best quality schedule, the least frustration, that's very valuable. So So quantum computers can harness these effects as these resources to help us solve these problems in a way that a classical computer can't when it's just stuck trying to break it down into steps of addition and multiplication.
Now, none of my listeners want to hear about Einstein and Schrodinger's cat and all this complicated description of quantum computing. What they want to hear is that I have a massive problem and I want to optimize and get a solution. And that's what we're talking about, something that can get a massive, for example, in the next 5 years, there's going to be 30,000 satellites up there. There's going to be debris. There's going to be collisions. There's going to be, I mean, that is a very complicated problem. That may reach the limits of what we call classical computing. Seems like that's a real good application for something that can optimize very complex system.
Yeah. And when we're talking about quantum computing, people are still trying to create an idea in their mind of like what it is that they're interacting with. And when we can put it to work for us, then we're starting to get a sense of the technology through the applications that it actually runs. So, for instance, like Pattison Food Group, I mean, just to try to bring this down to like really real world applications, a retail grocery chain is using our technology to schedule their at-home grocery delivery fleet. And they've saved 80% of the time in producing those schedules by using our technology to drive that application. They've expanded into their in-store workforce scheduling, creating an auto scheduler there. They're anticipating to save 50,000 hours annually in time saved. And the workforce time that's being saved are the team members who have the most experience, the most knowledge about the business, which means that they're able to get out of the back office away from their computers, doing a task that was kind of a grind for them, out into the team and start training other employees and working with the customers, which is what they're working in that industry for. So, in applications in the public sector, whether we're talking about, emergency response or whether we're talking about, national defense or transport or construction, infrastructure construction, those are opportunities to, better use our resources, better use our time, and to better use our energy to be more effective. And that's what we need if we want our economy to be more productive, if we want to make better allocation of these resources that we have. This is a technology that can help us with that.
I'm taking notes. I'm writing down logistics. I'm trying to figure the application for federal agencies. United States Army, do you think they have logistical challenges? I mean, just take the Air Force and logistical challenges. I mean, the Air Force has got 20 people just trying to project out fuel consumption. And that's a real challenge in of itself. And so I think if my listeners can understand quantum is a tool for complex problems, and I think if you have a complex problem, this may be worth considering. I think, and maybe do a test drive on your system, huh? dwavequantum.com.
Yeah, I think, for example, just like you're describing, the Australian Department of Defense looked at an application that had us build a proof of concept on how to use our technology to help them route vehicles for Army resupply. And so whether that's actually in a deployment or whether that's in an emergency response scenario, they were looking for, they've got multiple vehicles, maybe different modes of vehicles. They're having to run over roads of, changing, quality or accessibility in order to make sure that they're hitting and getting people out to and the resources out to the people that they need. So that's a great example of an application with logistics. And when we're thinking about this at like a federal level, the difficulty is that the problem scales are enormous already. When a small business is dealing with this, they begin with 2 or 3 employees, and then at that point the problem is solvable. That's the pernicious nature of these problems, that they start out easy, right? And then they become explosively complicated, even when you've got like 20 employees and like 200 deliveries that need to be made. What's difficult is that as they grow, humans tend to respond by trying to segment the problem. They break it into pieces. They start to create policies and sort of separating things out to control the complexity, so that by the time you get to a really large organization or like a large system of this kind of deployment, they've got some very hard rules in place that make it difficult for them to innovate. They become fragile. They're inefficient. They're trying to be responsive, and then they've just got a lot of frustration in their workforce. Like, that's not the way we do things. So when we're able to bring solutions in and describe how we can, take in these multiple factors and help them optimize, it really makes a difference. So, and it's not just a difference in terms of the overall effectiveness and the value that's bringing, but also in terms of like the human-centered approach. The frustration is dramatically reduced. And when we worked with IPG, they were planning promotional tours across the continental United States, and they had federal regulations and customer requirements. They were manufacturing, packing, and shipping all the equipment themselves. It required the coordination of multiple teams, and that process was taking them weeks. but they were able to just describe to us what they needed to get done, and we were able to put that into a program that took that process down to under an hour. So, when you can get that kind of transformative change, it's, the workforce is actually like drawing the technology in. They're delighted to get these easier solutions, and the organization can now use, instead of like doing these things way ahead of time and using stale information, they can start, running and rerunning much closer to the operating time, and that actually gives them a lot of power, a lot of competitive edge, and that's the kind of thing I think we need at the in the public sector, across the United States and North America.
Middle August, I'm flying to Columbus to a bunch of videos, and people love videos. And before this interview, you said that you were at a conference in Boston, and there's a bunch of videos that your company has that people can maybe get a sampling of what you do. So tell me about this conference and what kind of videos can they watch?
Yeah, so we have our Qubits Quantum Computing Conference was in Boston, June 17th and 18th this year. And we had a number of our customers coming out to talk about the applications that they were working on. So I think that's very compelling, because you get a chance to hear people describe their experiences, describe the advantages that they're seeing, and the way they're putting it to use. And a big part of the reason why that conference got organized is because our customers were saying, hey, I want to be able to talk with other users of your quantum computing systems so we can share lessons learned, and talk to one another about, how to get the best advantage. We had a public sector panel there with panelists from Deloitte, from the Department of Engineering, from Artificial Brain, and the Assembly of Digital Innovation. And they were talking about public sector use cases and how they can sort of learn lessons from the commercial sector, to use our quantum computing sectors to advantage there. And Davidson Technologies was out talking about applications that they've looked at in terms of like phased array radar scheduling. So that's scheduling the radar so they can be communicating with moving objects. And they managed to increase the utilization of that equipment by 15% on average. And also interceptor allocation, optimization assignments. And that, those are fantastic applications. They're about, helping to keep us all safe from a national security point of view. Especially given the worldwide events that are taking place. And they're also, at that Qubits conference, they announced that they're going to be installing our second US-based quantum computing system at their headquarters in Huntsville, Alabama. So I would check those out, take a look at that public sector panel, because I think that there's going to be lots to watch and listen to there that will broaden even, the area that I'm an expert in.
I think about 10% of our listeners know what a phased array antenna is. I happen to know that, and probably 1% know about quantum encryption and really complex topics. But I want to just a little bit of complexity here. I don't want to really delve into some of these serious issues, but let's talk about this contrast you have between a gate model and if it's contrasted with an annealing model. What are these two different concepts we're talking about?
Yeah, so it really centers on this idea of like, quantum effects. How are we going to use those as a resource for computing? And so different groups kind of came up with different ideas. And there's a sort of quantum information science group that came up with a gate model. It was inspired from classical computing. So in a classical computer, you have what's referred to as a memory register. So that's like a series of bits that you can use to keep track of a number. And then you can perform operations on those bits like addition and multiplication, like I was talking about earlier. So if they were thinking, hey, let's make a quantum mechanical version of that. So let's make the memory register a quantum memory register, and let's make the operations, quantum operations. And that turned out to be really interesting in terms of the development of techniques for quantum chemistry, for fluid flow and fluid modeling types of calculations. It's powerful because the computer is allowing you to put information into the quantum states. But what's interesting about that is, quantum states are famous for being fragile. So if the quantum state collapses, then that information you put there gets lost. So in that model, you have to have some fairly sophisticated error correction in order to be able to keep those operations running. And for that reason, those applications for that model in terms of, quantum chemistry, those are a little bit further out. We're projecting, 6 or more years before they sort of hit commercial impact. In annealing, the model was a lot more pragmatic and practical. It was really about how can we use quantum states as a method for just getting to better solutions quickly. It turns out that it's able to use quantum effects to move between solutions. So I'm talking about delivery drivers. If you just randomly assign delivery drivers to deliveries, you need to make swaps, in terms of like, I'm going to take Alice off of this delivery and put Bob in her place, so that Alice can go make a delivery in some other place. Those, each time you reassign drivers to deliveries, that's another solution you want to consider. And even if you just had 300 assignments to kind of consider, there's more possible schedules than there are particles in the universe that you could use. So being able to move between those solutions more quickly with annealing turns out to be very valuable there. And at D-Wave, we're famous because we're building both of those models. We made a really early move in annealing, and that was because, as you mentioned, we've been around for 25 years. We were studying the technology really early on when it was largely, in a research department or it was in universities. And we were looking at how do we holistically build a computer? Because a computer needs to do work for us. It needs to be able to, run applications for us. And we realized that with annealing, we had access to near-term applications. The systems were going to be easier to build, and you didn't need to know quantum mechanics to program them. So those were three very strong reasons to move in that space. And that's exactly why that model of quantum computing is driving today's quantum hybrid applications, because it's scaled much more quickly. The applications are more accessible, and programmers are finding it easier to use.
Let's say someone from the federal government is listening to this and they have a scheduling problem. They have a problem with radar and they want to purchase some services or get some consulting work for you. So how can the federal government purchase quantum?
So any federal agency can purchase quantum computing from us right now. They can absolutely, reach, I would say, send an email to sales@dwavesys, or connect with me and my LinkedIn account. And we have cloud access on our Leap Quantum Cloud platform. They can create an account there. And then that's what gives them access to the quantum computers when they want to do direct programming, and also the quantum hybrid technology for when they're quickly building applications. And so I think for many people, it's surprising how easy it is, to get access to it. When I was at the Reuters Supply Chain USA conference in Atlanta, Georgia, I was talking about these applications that people were using and the transformational impact it was having for their businesses. And they were like, how is it that I don't know about this already? Like I thought quantum computers were 5 or 10 years away. And that's the difficulty. It's a space, it's a domain where I think a lot of different people are kind of, giving different perspectives. So it hasn't settled out. It's not at the point where you're hearing a consistent message from everybody. So definitely, I've been working at D-Wave for over 21 years. I'm trying to help people see the forest as well as the trees, so they can see how to use the technology and take advantage of it today.
I think it's a Star Trek effect. If I walked down to the 7-Eleven and I said artificial intelligence, everyone, let's talk about it. But if I said quantum, they go, ooh. Nimoy, Spock. I mean, it's scary. It's, I don't know why artificial intelligence doesn't scare people. It's fun, but quantum is like, oh, wow, you got to be Einstein. And I think it's just maybe it's a public relations Is it a public relations problem of, that word is so scary, is so associated with quantum solace and James Bond, and all these very complicated things. So maybe it's got a public relations problem. Is that it? Maybe that's the answer, Murray?
Well, I think, I'm talking to people, I've definitely talked to folks for whom technology itself can be scary.
Yeah.
And artificial intelligence, I mean, I've certainly talked to a lot of folks who are at least set at unease with the way that the technology is developing, but that's largely because it's unfamiliar. I mean, the notion here is to make computing systems act more intelligently in a way that we do. So there's some degree of familiarity there. But quantum systems, it's not something that people normally interact with. That's why I'm trying to let them know that they can actually start doing that right now. But it's quite a deep space. It's taken us a while. There's quite a lot of technical skills involved in kind of like really sort of like describing the way that the systems work. However, we're entering a stage here where you can actually just build the intuition from interacting with it, rather than taking like a formal academic approach to quantum computing. You can actually just sort of saying like, hey, I don't understand everything about the computers that I use, but my kids certainly know how to like download apps and like, log into platforms much more quickly than I do. So I think by being able to interact with quantum computing, we can develop an intuition for how it's a tool for us, how it can do useful work for us. And, the other thing is, we've entered a time now where the technology is outpacing, our ability to kind of like catch up to it and put it to use. Like it's already being used by organizations. It's bringing people value. People can build applications with it relatively quickly. we've been able to show and demonstrate in scientific papers that we can improve solution quality faster with quantum computers than with classical computing technology. So now we're in this race to sort of like catch up. How can we train our workforces quickly to learn how to use the systems, right? We have professional 1 week programs to get people up and running on that. How can we, start incorporating this in our applications so that as the technology continues to develop rapidly, we can see that compounding benefit in the applications and the operations that we're orchestrating.
Well, whether my listeners like it or not, they're going to have to learn about quantum because the federal government has some specific initiatives in that regard. NIST, all those brainiacs up at NIST in 2016, they started talking about, cybersecurity and quantum. And there's been acts have been passed, and there's some serious discussion now about cryptography being applied to quantum, and people have to understand that. Now it's in a future date, but still, these are serious issues that I think just this conversation today, I think your focus on use cases really helps people think about it. And the use case, of course, is cryptography. It's another use case for it that we could go 5 hours on that. But I think what's going to happen, people are going to have to be much more fluid and glib with their understanding of how quantum can help them.
Yeah. Well, I think, let's think about the direction that quantum computing is going is where classical computers are today, right? It's threaded through the fabric of our society. All of us are using the technology at different levels in order to be able to help us do useful work. It's part of our education system. Kids learn about it in elementary school and high school and then in university. That's where quantum computing is going. And it's not the kind of thing where each individual has to become an expert in the quantum technology itself. A big part of the reason why we built our software development kit for programming our systems in Python in the open source is because different users are coming at it at different levels, right? We've got physicists who are programming it at a machine instruction level. We've got mathematicians who are programming it in the abstraction layers and building systems that make it more efficient to use in a hybrid context. And then we've got software developers, Python programmers on application development teams and businesses who are building applications with it. So they're coming in at the top level of that technology stack. And what's great about that is that the businesses who are running those applications, it doesn't matter if the hardware gets upgraded, if the physicists come up with a better machine instruction, if the mathematicians come up with better representations, they get a compounding benefit from all of those changes. So that's what's making this development very rapid in terms of benefiting folks. And when I'm talking with organizations, we're working with them to help them with the change management process of building applications and getting them up and running in production. That doesn't happen overnight. Regardless of what technology you're building, it's going to take weeks or months to actually get production applications up and running. And certainly if you're using like large physical systems, like you're managing operations at a port, you've got a whole fleet of employees that you need to train on the new systems that you're putting out. That can take a year. So it really is the case that people need to get started quickly because we've already got these cases like the Port of Los Angeles using our systems working with Savantex to increase the amount of cargo they're handling at Pier 300 by 60%. And that's a dramatic increase, right? And that has lots of applications where we've got groups who are working in a fixed operating theater and they just need to, better manage the logistics and the operations within that theater. That's exactly the kind of thing that the port is facing. So I've seen, let's say, the Quantum Algorithms Institute here in British Columbia is running a program for all, staff, faculty, and students from Canadian universities, basically saying if they want to get upskilled on programming our quantum computing systems, they will basically get them enrolled in one of our classes. It's a 1 week class to kind of get up and running and learn how to build applications with our technology. That's the kind of thing that, when I'm talking to folks in the public sector, they're thinking about, how do we get our workforce upskilled? How do we get our businesses using these systems? Because then they can respond more quickly to change, faster speed to decisions, and they can use their energy and their resources, their time more efficiently. Because we need to get our productivity up. We need to be able to do more with the resources that we have. And I think that's for, there's so many benefits we can see there, both in terms of like our own quality of life and then also in terms of, being able to keep people secure and keep capital and equipment, flowing in manufacturing.
We've just scratched the surface on this. When you said energy, I just flashed on Department of Energy's got a whole initiative involved with quantum. I mean, there's so many topics. I mean, we could do 3 hours on cryptography and quantum. It's so many different aspects, and I don't think people are understanding it. But I think the whole idea of telling the story visually and having a video, and what I'll do is for the listeners' benefit in the show notes, I'll put a link to a little video, especially with the federal agencies and the use cases and how they can apply it. So maybe the next time we'll take the next mountain, or maybe like another mountain range, because quantum surely is it's just too incredible. You have been listening to the Federal Tech Podcast with John Gilroy. I'd like to thank my guest, Murray Thom, Vice President of D-Wave.